So, did everybody see the email that went out about the homework assignment? So this is a custom brewed homework assignment because we are not operating out of the book at current, although I believe by Monday we should be back to just reading out of the chapters. So I'm excited about that. It'll be a little easier for me. But in the meantime, I was definitely getting the sense that we needed some more like practical, hands-on. So I gave you, I think, 5 problems and asked you to do 3, subject to the limitation that you don't do both the first and the second one. You could do one or the other. You could do neither. Just don't do them both. Let me have a look here. Now, having said that, the only reason I said don't do all 5 is because they're time-consuming, not because they're not important. So my feeling is that you should try to do all 5 at some point. Definitely before any test that we may or may not have in 2 weeks. So, read, and do problems. They're good for you. That's kind of my feeling. But anyway, I tried to really give you a taste of everything. All right? Questions? So today, we're going to kind of finish the example from Wednesday with the hope that we can do like one end-to-end example, and that'll hopefully help you a little bit on the homework. So to remind you of what we were doing, so we're having this conversation that there's, so not all filters are the same. So not all filters are equal. And there's sort of the 2 flavors that we looked at were Butterworth. And actually, I don't remember the second flavor I showed you. Was it Elliptic or Chebyshev? It was Chebyshev. All right. Okay, so this is Butterworth and Chebyshev. And like I said, I don't... Yes, sir?
Between the transfer function and the characteristic equation.
Yes.
Which one gave more detailed information about that?
Same thing. They tell you the same thing. So it's a good question. I'm glad someone's asking this question. So the characteristic equation. So the characteristic equation, you get first you find the differential equation for the circuit, right? So you get the differential equation. So for example, if you just think about the regular old low-pass filter that we looked at. I always like to use that as my example because it's simple and we can kind of wrap our heads around it. So it had a differential equation that was the derivative of the output voltage plus the output voltage over RC equaled the input voltage over RC. Is that correct? Okay. So then what we did is we took that and we used that to generate the characteristic equation. And the steps we did were we looked at the coefficients for each of the terms in the differential equation. And on the output side, we just set it equal to 0. So we said, suppose there's no output. So here the coefficient is 1 times S. And here the coefficient is 1 over RC. And if there was a second derivative, it would be S squared. If there was a third derivative, it would be S cubed, and so on. Okay, so basically you just pulled out the coefficients, and that becomes your characteristic equation. You solve the characteristic equation, and then that's how you that's how we got, for example, the step response. Okay, now, so the solution to this is S equals minus 1 over RC. So that means that your step response was, in this case, turned out to be 1 minus, okay, so there's that's your S. Okay, and this is your, okay, so anyway, that was the characteristic equation. I don't want to get too lost in there. Okay, now, separately, let's say that we did the transfer function for this thing. When we did the transfer function, remember we said this was an impedance of R, this was an impedance of 1 over j omega c. And remember, I introduced this concept that for j omega, we'll just use the shorthand. We'll call j omega equal to S. just to make it easier when we have like multiple terms. And we did the voltage divider. And when we did that, we got the transfer function which was, in this case, I think it was 1 over SRC plus 1. Okay, and then we said that the so we said this is a low-pass filter, and if you want to know where the low-pass filter cutoff frequencies are, you solve for the poles, right? The values of the denominator, the values that set the denominator equal to 0. So set denominator equal to 0. SRC plus 1 equals 0. S equals minus 1 over RC. So, which gave you more information? The transfer function or the characteristic equation? It's the same thing. It's the same equation. There's only one equation, right? That's my point. S plus 1 over RC equals 0. SRC plus 1 equals 0. It's the same equation, right? If I just divide this equation through by RC, I get that one. So I'm happy to talk about it because I think it's kind of an important point. Like there's no difference between the knowledge that you get from the characteristic equation and the knowledge that you get from the transfer function. And the reason there's no difference is the circuit only behaves in one way, right? It's not like there's 5 different ways of explaining the same behavior. It's like, that's it. There's one thing that it does. There's this number, 1 over RC. If you know that number, you know everything there is to know about this filter. You know its cutoff frequency, if you're thinking about it in terms of a filter. You know its time constant, if you're thinking about it in terms of a step response. Okay, so that's it. There's only one equation. So in all cases, if you know the transfer function, that's the same as knowing the characteristic equation. They tell you the same thing. Yes?
Is not this one starting and then the other one frequency domain?
Well, it turns out that once... No, they're really still telling you the same thing, though. It's not... I mean, this was a time domain analysis, but effectively when we did this, we effectively converted it to the frequency domain. I don't want to get too tied up in that because those are words that... I mean, they mean different things, and I don't want to... But they're basically both a frequency domain analysis, to answer your question. Yes? Yes, absolutely. And the only reason I do that is that if I don't do that, when I get to more sophisticated circuits that have, let's say, an inductor and a capacitor, or 2 capacitors, then if I don't do that, then people start to panic. And if they have like 2 j omega terms and they multiply them against each other, then they're like, oh, that's equal to minus omega squared, which is true. It just makes the math ugly as anything. So instead, you just leave it as s's, and then they're easy to multiply together. There was a hand somewhere. Yes, sir?
So if I have a circuit with the characteristic equation and I calculate the voltage division, the transfer function,
Yeah.
and I'm not getting the same coefficient, something must be wrong. Right?
Something is wrong. Yes, you should get the same thing. No, it's good. I mean, it's a good sanity check because you should be comfortable doing it both ways and getting the same answer. And if it's not, that's like a good opportunity for you. Like, I'm happy that you at least have enough insight to say, wait a minute, that doesn't make sense. So now you should go back and figure out what doesn't make sense. Like, is one of them incorrect or both of them or whatnot. But yeah, they should tell you the same thing. Absolutely. How are we feeling? This stuff's not trivial. I mean, I'm asking you to do some heavy lifting. It's okay. We good? All right. So the lesson from Wednesday was that there's different kinds of filters. All right. And I don't care. I'm not trying to teach you how to design these filters. I'm not trying to teach you the math behind them. All I was trying to say was that for a given order, like let's say you're going to make a 3rd order filter, there's a difference. Like you can get different performance kind of depending what your behaviors are. Okay? So I think that we found that for a Butterworth filter, if you look at it versus frequency, the Butterworth filter tends to roll off. It has really nice performance in the pass band. The Chebyshev filter, by comparison, did something that looked like this. Like roughly correct. Okay, so the Chebyshev filter had some wiggles in its passband performance, right? Some frequencies got a little bit better than other frequencies in the passband. But I said if you were capable of tolerating those differences in passband behavior, then you can get much better performance in the stop band for the same filter order, right? We said like, oh, for a third order function, one of them performs much better than the other one. Okay, so that was kind of that was what I was trying to demonstrate. And there's always software that, like, you don't actually have to learn any of these equations. There's always software tools that say, oh, you want to build a third order Chebyshev with a cutoff frequency at 1,000 hertz? Boom, it'll just tell you where your poles are. So I did want to finish the example that we were doing, though. So unfortunately, I don't remember all the details of it. So we were trying to build a filter, and I remember it was third order. And where were we trying to get the overall cutoff frequency? I remember we had 3 poles altogether, didn't we? Right, we had 3 poles. And the software told us that if we could build a circuit that had those 3 poles, we would get a cutoff frequency where?
Negative 628.
628? Okay, so the circuit cutoff, was that right? Negative 628? Okay. So that would be the cutoff frequency for the entire circuit. All right, so in hertz, that's all right, because that was 100 hertz. I think that's right. That's the same as having a cutoff frequency at 100 hertz, right? If you take 100 multiplied by 2 pi, you get 628 rads per second. And it was a Chebyshev filter? Well, Sallen-Key, okay. Sallen-Key was the style of circuit that I was using to implement my filter. Why don't we back up and sort of take this example from the beginning? Then I think that might help for a little bit of clarity. And now that we're done actually deriving the circuit, hopefully that won't take too long. If I can clear your quiz off the screen before the projector comes up. Yes, I saved it. Okay. So, while we're waiting for that to burst into life, okay. So let's do this example from scratch. So, okay, so everybody remember this plot? So remember we said we decided we were going to ignore the blue signal, the blue trace altogether, because it was just a lousy filter with no redeeming qualities. But if you look at the red and the green, that's the Butterworth and the Chebyshev. And keep in mind, do they both have the same cutoff frequency? Yes, they both have the same cutoff frequency because they both pass through minus 3 dB at 10 squared, 100 hertz. All right, but we said the Butterworth filter is not as good as rejecting frequencies as the Chebyshev filter, right? At any given frequency, right, the Chebyshev filter, the green one, is giving you more rejection than the Butterworth filter, even though they're both, in this case, third order filters. You with me? Okay, so I do want to summarize what we're looking at. So we've got third order filters with a cutoff frequency of 100 hertz, which is the same as saying you have a cutoff frequency of 2 times pi times 100 hertz. So that's 628 rads per second. Is that correct? That's what we're looking at. Now, in the case of the Butterworth filter, okay, in the case of the Butterworth filter, the 3 poles that I need to make that filter are shown here. And in the case of the Chebyshev filter, the 3 poles I need are here. Okay, so I want you to see that. The poles are in different frequencies. All right, even though both of them yield a third order filter with the same net cutoff frequency, in order to build those frequencies, those filters, I need very different sets of poles. I'm actually going to try to write those down. Let's see here. H butter. Okay, so for the Butterworth filter, my poles are at, so my Butterworth filter poles are at 2 of them are at 628 e to the j. Oh, let me just tease this information out of here. Plus or minus 2.09, 2.094, and then a third one at minus 628. So let's just look at so all I've done here is I've actually had MATLAB tell me specifically what frequencies those are at. And this is the part that I don't really care. I'm not trying to teach you this, okay? But there's a formula somewhere that exists. MATLAB knows it. We don't have to worry about it because it's built into a software package. But all I had to do was go to tell MATLAB, I want a third order filter with a cutoff frequency at 100 hertz. Where's the poles at? And MATLAB says, boom, you need to put your poles at these frequencies. So they're at 628. So I've got 2 complex ones. Those 2 complex poles expressed in polar form are at 628 plus or minus 2.09 radians. All right, does that make sense? 2.09 radians compared to what you're seeing on the board? It's a little bit more than 90 degrees, right? And this is 0 degrees, 90 degrees, a little bit more than 90 degrees. Is plus or minus, is 2.0 radians a little bit more than 90 degrees? How many radians is 90 degrees? Pi over 2, which is about 1.5. So it makes sense that if I'm getting 2.0 radians, this is 1.5 radians, there's 2. So that's good, that makes sense. So I've got plus 2.094, and then this one is minus 2.094. So those are my 2 poles. And then I need a third pole at 628. All right, so that's what that's telling me. So if I can physically build a circuit that has these 3 poles, I will get a third order Butterworth filter with a cutoff frequency at 100 hertz. Now, supposing I decide to build a Chebyshev filter. Chebyshev. So same thing. Third order, same cutoff frequency. But in this case, my poles are going to have to be at different frequencies. So here it looks like .575 e to the plus or minus j 1.7 and then a third pole at negative 188, negative 187, whatever. We're not going to split hairs over one pole, over 1 degree. Okay, so what is so basically I just had to give me the locations of those poles. So again, I've got 2 complex conjugate poles and 1 real one, and it's telling me these 2 complex conjugate poles are at a magnitude of 575 and a radians of plus or minus 1.7. Does that make sense? The 1.7. Is that consistent with the graph? Yeah, because remember we said 90 degrees is a shade more than 1.5. And I've got 1.7, so that's just a little bit after that. Okay? And then I've got my real pole, which it's telling me has to be at negative 187. So isn't it interesting? I think it's interesting that, I mean, this is a 3-pole filter, and this is a 3-pole filter. And they're very different poles. And yet both of them will give me a 3rd-order filter with the same cutoff frequency. And now I get to pick, right? I get to say, oh, in this particular instance, I really need something that has the Butterworth filter performance. I really want it nice and smooth in the passband. Or I could say, screw the passband. I'm not too picky. What I really need is great performance in the stopband. I'll build the Chebyshev one. Okay? But in terms of circuit complexity, they give me the same thing. Are you with me? Good. So, I think I can park that for the time being. Let's just put this on mute in case I decide to use it again. All right, so now we get to the issue of the Sallen key filter. So the Sallen key says, cool, let's actually build a circuit that does that, right? Because at the end of the day, this course is called circuits, right? It's not called equations on a chalkboard. So I mean, we can write equations all day, but, you know. So my question to you is, how do we actually build this? All right? And that's the investigation that we started on Wednesday, right? So on Wednesday, I said, okay, what we're going to do is, first we're going to build a first-order filter, right? The first-order filter will give me my first-order pole. And then I'll daisy chain that onto a second-order filter, which will give me my 2 complex conjugate poles. And if I pick my resistors and capacitors correctly, which I'm going to, I will be able to get my poles at exactly these frequencies. And I will have succeeded in my eventual goal of building a circuit that does something useful, as opposed to writing a bunch of equations. So let's go through the exercise of building a third-order Chebyshev filter. All right. So we're gonna implement the Chebyshev filter. Now, and just to start things off easy, why don't we just start with the let's just start with the first order. Okay. So how do I build a first-order low-pass filter? RC circuit, right? Even I know that. Okay? So my first order circuit is going to be an RC circuit. How can I select my values for R and C? What's my criteria? So what's the cutoff frequency? What's the characteristic equation for this circuit, or the transfer function? I guess I don't really care. It's 1 over SRC plus 1. I don't need to rederive it. I think we've seen it a few times now. So the transfer function for that circuit is 1 over SRC plus 1. So what's my value? Where's my pole? SRC plus 1 equals 0. Therefore, S equals minus 1 over RC. Cool. Where do I want, what's the actual number where I want my pole to go? That frequency, negative 187. Why? Because I'm trying to pick off a single pole, a single real pole to build my Chebyshev filter. We together? We in the same place? A lot of blank stares. I know it's Friday and you're all scared about the hurricane. So we got to power through this. Temple's built on high ground and we never close. Unfortunately, the subway will be flooded, so I don't really know how I'm going to get here. Okay, so how do I pick RC? I mean, this looks tantalizingly useful, doesn't it? So help a guy out. What am I going to do? Pick a value for the capacitor. All right, I always like to pick a microfarad because it's a nice round number, and you know, that's just me. But you pick whatever you want. So I'm going to pick at random. I'm going to pick the cap to be a microfarad, and therefore that's going to force my hand for the resistor calculation. So let's see. My resistor is going to equal 1 over 187 times a microfarad. So I'm getting like 5.3 kiloohms. Can I get a confirmation?
Yeah.
Okay, so this is about 5.3 kiloohms. My calculator actually says 5.3476. Am I going to write all those numbers down? No! Good luck going to the resistor bin and finding a resistor with value 5.3476. Okay, remember resistors always come with plus or minus 10% anyway, or 5% or whatever. So don't get, you know, don't try to impress me with like 8 decimal places here. It's meaningless. Okay, how are we feeling? Are we good? Nice. So we picked off that pole. Good. So I'm a third of the way to my eventual goal of building this circuit. Am I not? Cool. Now I got to get 2 more poles. How should I build those 2 poles? Can I build another RC circuit? RLC. Okay. Well, first of all, let's just start with the disqualifying question. Can I use this circuit to get me these poles? No. Why? There's an important reason. This circuit can only generate real numbers. Look at this. S equals minus 1 over RC. There is not a J to be seen. There are no square roots of negative 1. Seriously. This filter will only produce real poles. I've got my real pole. Now I need to deal with complex poles. How can I get complex poles? I've got 2 choices. Choice number 1 is to do an RLC circuit. But as I tried to make the case on Wednesday that although mathematically that works out, from a practical standpoint it leaves a lot to be desired because it's very hard to daisy chain those circuits together without an op-amp in between them. Okay? If you daisy chain them together without there being an op-amp, then one circuit will affect the performance of the other circuit and all your poles will not be where you think they are. So instead of that, we tend to follow some other circuit topologies that have a better performance. So that's where we come into play with the Sallen key filter. So the Sallen key is not so much a filter, it's a type of circuit. The same way we call this an RC circuit, I'm calling this a Sallen key circuit. It's a filter, okay, but I want you to differentiate between Butterworth and Chebyshev is a way of picking where your poles are. Okay? Sallen key is a way of locating your poles. So, on Wednesday, I gave you sort of the entry-level Sallen key, which we are actually not going to use because it turns out to be not all that useful, and I'll tell you why in a second. So we built this circuit. Okay? Don't even copy it down because we're going to erase it, or we're going to modify it momentarily. And I tried to make life easy for everybody by forcing the cap and the resistor to have the same values. Is good? All right. And then we did a big old derivation. We filled like 8 chalkboards. And after everybody lost the will to live, we came up with the following. We said that the transfer function was equal to, I believe, 1 over RC squared times S squared plus 2 over RC S plus 1 over RC squared.
Just RC
That's consistent? I may have written, is it? We can vote. We can be democratic. I'm cool with that. I'm liberated. Okay, good. All right, sorry. We're going to go with this. Okay. I'm a reasonable guy. We can vote. Okay, so this sort of works out, except there's a problem. So remember, the idea was that we were going to match. We know that this always has to have the form. We know that this always has to have that form, right? Our denominator. So this is good because we can pick our omega naught. Right? So I can pick my RC to get me my desired value of omega naught. Unfortunately, when I do that, my zeta is for this configuration, my zeta is 1. This always produces a circuit where zeta equals 1. So that's not really helpful to me because I don't want zeta to be 1. I want zeta to be some other value. So what I'm going to do is, and I'm not going to derive this for you, I'm just going to tell you the answer, and I've typed out the derivation and I'll post it online, and if anybody cares, you can look at the derivation. But essentially, I'm going to make a very small change to this. So you guys remember how that buffer that I've just erased had a gain of 1? It was like output equals input. I'm going to change it ever so slightly. You guys remember that circuit? What is that? It's a non-inverting. It's a follower with a little bit of gain. Okay, so what I'm going to do, I'm going to label this R2. I'm going to label that R1. And I'm going to say, just for this circuit, let's just say that has a gain. Does anybody remember the equation for the gain? 1 plus R2 over R1. It's like we taught you this stuff for a reason, okay? Okay, so if you do that, we didn't change the circuit much, right? So you shouldn't expect the transfer function to change much. Turns out all that changes is you get a gain term upstairs, which is nice. And this 2 turns into a 3 minus gain. Okay. Have you lost your will to live yet? The good news is this is probably going to take long enough that we'll have to punt your quiz till Monday. So, you know. That's good, right? Yes. And maybe the hurricane will get it punted till Wednesday. I'm sorry? Where? G, that's just gain. There's no conductance or admittance. It's real. There's no imaginary terms here. No, you're good. You're good. Okay. So, here's my challenge to you. All right? We've got to pick R, C, R1 and R2 such that I get that. Those are my roots. Help a guy out. It's definitely going to be complex. What's that? Right. Well, I've got, no, that's right. So each one of my, so if I were to factor this, if I were to apply the quadratic equation to this, I should get, the solution to that would be those two poles. That is the ugliest way to do it, but it will work. So I'm going to employ a little shorthand. I don't know if you know, I'm not playing games, but we talked about this. Do you remember, it turns out that when you have complex poles, I'm just going to rewrite this over here just so we can have it closer to where we're working. So my poles are at 575 angle plus or minus 1.7. So I think we had this observation that this number will always be, does anybody have it? That number will always be omega naught for your circuit. Okay? Yes, sir?
What's the same side of the parentheses? The next equation number.
To the here? 3 minus g. So it turns out that if we were to take the roots of this equation using the quadratic equation, and what you would find is that the roots of your quadratic equation expressed in polar form, this number here would be omega naught. So that's like a little shortcut to get you to your answer. Okay, so in other words, what I'm telling you is that by matching, we know that omega naught squared has to equal, has to equal 1 over Rc squared, which means that omega naught has to equal 1 over Rc. And I've just told you that omega naught has to be the absolute value of your roots. 575. Ooh, we're getting close now. Yeah, pick a capacitor. Okay, we'll pick the obeyed default value of 1 microfarad, available in every capacitor bin. All right, and what's that leave me with for a resistor? Should be 1 over 575 times a microfarad. I'm getting like 1.7K. We're getting very close. Yes, that is a coincidence. Don't scare me like that. That's kind of, yeah, that's kind of weird that works out. Okay, now we get to the tricky bit. We still have to get our gain. I guess I'm going to erase this now. So, if we match the middle terms, let's see what that gives us. That tells us that 3 minus g over Rc equals 2 zeta omega naught. Hey, look at this. Is it true that omega naught is 1 over Rc? Yeah. So I can set this equal to this. RC's cancel. So that means my gain should equal 3 minus 2 zeta. Friends, this is ugly, but we're going to get to someplace useful. So it seems to me that if I knew what the value of zeta was that corresponded to these roots, right? If I knew what that value of zeta was, I could then come and sub that value of zeta in for here, figure out the gain that I need, and from there, pick values of R1 and R2 that would give me that gain. Is that not right? So all I need to do is to determine what my value of zeta is. Yes, sir?
That top one of 3G RC, could you just go through that one more time?
So this expression here is the transfer function for this circuit. I did not do that derivation. I just kind of gave it to you. I'm going to post a derivation if anyone cares. On Wednesday, we derived a simpler version of it where the gain was equal to 1. Okay, but we know that for a second order circuit, the denominator, right, the characteristic equation always has the form s squared plus 2 zeta omega naught s plus omega naught squared. So all I need to do now is pattern match, right? I know that the constant term of the characteristic equation has to equal the constant term of the characteristic equation. So I was able to set those two equal to each other. Likewise, the coefficients of the s have to match, right? Because it's the same thing. So that's it. I just set them equal to each other. I was fortunate and the RC went away, so now that's all I'm left with is a relationship between the gain and the value of zeta that I need. So can we figure out the value of zeta that I need? So in other words, what value of zeta does this represent? How could I know that? What's that? It's got to be between 0 and 1, absolutely. But how can I know for sure? We talked about that, right?
There's a complex number. It's under them. It's, we have complex. Yeah, and the under them is 0. Between 0 and 1.
Right. Okay, but I need a value. I mean, I know that zeta has to be between 0 and 1. But I need to know which value of zeta, right? Not just that it's between 0 and 1. Like, I actually need a specific value. So how can I look at these roots and determine what's the specific value of zeta?
Zeta omega equal.
Say again?
If you do 2 zeta omega naught equals that?
Equals the, no, you can't do that.
Yeah, we can make that as a rectangular form and we can make 2 zeta omega equal the real part.
2 zeta omega is the real part. Okay, so let's kind of backtrack a little bit. I think the rectangular form might be helpful. So, sorry, go ahead. No, because there's all this other stuff that happens between voltage in. I mean, that's voltage in and voltage out of just this little sub-circuit. But now we're trying to. We need to know how to set the gain of this thing in order to get the entire thing to have the value of zeta that we desire. Right. So the problem that we're now having is, we know the value of omega naught. What's the value of? I need to know what's the value of zeta that's represented by this root. Okay. 2. We know for a fact zeta's got to be between 0 and 1 because it's underdamped, because it's complex poles. So let's say I'm stuck and I have no freaking clue how to proceed. All right? The best thing I can do is I can just revert back to like something I know for sure. So for example, I know my character. So let's say I actually go ahead and apply the quadratic equation to this. Right? So if I apply the quadratic equation, it's going to be minus b plus or minus the square root of b squared minus 4ac all over 2. and I think we've done this at some point. It's gonna simplify nicely. In order for this to be complex, which we're expecting it is, that means that the 4 omega naught squared has to be bigger than that term. So if I do that, first of all, 4, 4, that comes out as a 2, 2 and 2 cancels. So I'm left with minus zeta omega naught plus or minus j root, no, minus j omega naught, because omega naught squared factors out as omega naught, root 1 minus zeta squared. So if my answer were in rectangular form, if my poles are in rectangular form, this would be their form. Well, can I take my roots and express them in rectangular form? Totally. All right, somebody help me convert this to rectangular form. Let's see, can I convert this to polar form? This squared plus this squared is going to give me omega naught E angle, and it's going to be inverse tan of this part over this part. That's ugly. Okay. So, let's convert this to rectangular form. So it's going to be 575 cosine 1.7.
Which is minus 74.
Minus 74.
0.085.
Plus or minus j.
J.
So now it's going to be 575 times sine of that number. 570. 570, good enough. Okay, good. So now 570 has to be equal to your omega naught root 1 minus zeta squared. Do we know omega naught? We sure do. Right, so we've got omega naught root 1 minus zeta squared equals 570. We know omega naught equals 575. It ain't pretty, but we can solve for zeta. So let's do that before we call it a day. So 570 over 575. And I'm going to take that number and square it. I'm going to do 1 minus that number. And take the square root of it. Okay. So I'm getting a zeta value of 0.13. So to summarize, I had poles. I need to pick values. I need to basically figure out how to get my characteristic equation to give me those poles. So the omega naught was easy. I just picked that off by inspection. But there's a few steps I had to follow to get the correct phase angle. So what I did was, instead of looking at it in polar form, I expressed my poles in rectangular form. And I recognized that my rectangular form roots of my characteristic equation had to look like this. I set the imaginary parts equal to each other and solve for zeta. Yes?
Can you just do the equation match thing again and do -2 zeta omega equals -7?
Yes, that would even be easier, wouldn't it? Thank you. I'm not always the... Yes. Yeah, that would actually have been like 400 times easier and should give you the same thing. Right. You could also say that... minus zeta omega naught equals minus 74. Does that give you the same number? Okay, so let's finish this. 3 minus 2 times 0.13 has to equal my gain. So let's see. Let's figure out what is R2 over R1. So if I say 3 minus 2 times 0.13, so that tells me that so this expression equals 2.74. Subtract 1 from both sides. R2 over R1 is equals 1.74. Okay. Does it matter what values of resistor of what the values of R1 and R2 are? No, as long as their ratio is 1.74. So I'll say that R1 equals a kilo ohm and R2 equals 1.7 kilo ohms. Okay. I'll simulate this for you on Monday. As you're leaving, I do want to show you something, though, to convince you that this stuff isn't just jibber-jabber. As you're packing, let me see if I can find the actual page. Hey, look, everybody, it's chapter 3 of my dissertation. All right, this is a circuit that we built to process signals coming off a monkey's brain, right? Electrode go in the brain, you got to filter it, you got a low-pass filter, high-pass filter, gain. Guess what? You have all the tools you need to analyze this ugly circuit that appeared in my dissertation. Right? What's that? Sallen-Key low-pass filter. Sallen-Key low-pass filter. What is that? What do you think this might be? Sallen-Key high-pass filter, right? It's the same thing, just swap the caps and the resistors. It's a high-pass filter. So I've got, what's this over here? Cap and resistor. High-pass RC, okay? This has got some gain, but it's also got a filter in there. I don't remember. That's going to be a low pass. No, that's a low pass. Okay, that's a diff amp with a high pass filter. But the point is, you have all the tools to understand this circuit, right? If you understand how to do the math for each stage, you can daisy chain them together all day long and just make sufficiently more sophisticated circuits. So this is a circuit that's got low pass filters, high pass filters, and gain. It's basically a band pass filter with gain. So I amplify the frequencies of interest to me, and I filter off the frequencies that are not of interest to me, and hopefully the signal that I've got left is exactly what I want. All right, so this is like a fifth-order bandpass filter or something. But you have the tools to understand this. And if I added another 5 Sallen-Key filters, you'd know what to do as well. So it's all about just getting the values exactly the way you want them. All right, that was a lot. I'm going to try to type up my notes from today so that you can have something useful to study. But do the homework. Sorry to keep you a little extra.